This is good though, yeah. I have one more piece to add on.
I mean, because what I'm doing right now, 10 terms analysis is also pretty much
Homework assignment's gonna drop. I will be doing it on the train
That's what
tomorrow.
that's what I'm doing right now.
Yeah, I'm taking the train. I've had so many problems this week with the train, so I'm kinda scared. Yeah, thoughts and prayers. It's like a 3.5 hour. It's not too bad, but then when you get to Connecticut, there's like a speed limit restriction, so then it kind of gets delayed, and I'm like, how do you not factor that in? Yeah. I don't even know.
Okay, let's get going. Today, we're going to start to talk about hierarchical models. After we say this, although perhaps it should be pointed out that the original motivation that we had here at Columbia to start to create STAN in 2010, 2011 was to estimate hierarchical models better than the software of previous generation, Bayesian software, but better than previous generation of Bayesian software. But before we get into that, I wanted to put this up again, which is the price of a futures contract on who will win the Electoral College in November. And you can see, if you had not been keeping up with this market, that if you had thought that the probability of Biden winning back when the semester started, which was like around here, was higher than what the price to buy, or alternatively, if you thought the probability of Biden winning was lower than the price to buy, you could have bought either of those. And although it went kind of up after the semester started and then down for most of February, lower than what it was in January, if you had bought when the price for the Biden contract was somewhere around where it was when the semester started, you could have sold it today and made approximately a dime for each contract that you buy. And so, you know, why it is starting mostly in March that the probability as judged by people who participate in the predicted market has increased. The economy has done a bit better than we thought. Polling data has been more neutral, whereas previously it was fairly clear that Trump was slightly ahead in polls. All sorts of other reasons you could possibly think of as to why the price would change. But we know how prices are supposed to change based on what we've been learning this semester. In principle, people should be updating their beliefs about unknowns as new information comes in. And these futures markets give a way for expressing these conditional probabilities, conditional expectations. Whether these prices evolve according to Bayes' rule is something that people have looked at a little bit. At a minimum, you have to make pretty strong assumptions about the efficiency of markets and how, do you have sufficient volume on this and things like that. But I would say there's no particular reason why a particular market has to evolve exactly according to Bayes' rule. It should, but there's no rule enforcing it. Moreover, these futures markets like we have here are not the expression of belief of any one particular person. It's sort of the marginal, the marginal person. There's a bid and an ask, and when they overlap, then there can be a trade, etc. So these, to some extent, are a reflection of conditional probabilities. We know how, in principle, conditional probabilities should be dealt with or managed according to Bayes' rule. And, these futures markets, usually for something that's as well known as this, or sports betting, sometimes at least tend to go in the right direction as new information comes in, but whether they're moving by the right magnitude, depends on what you condition on, and it's not entirely clear who all is participating in this and what they are conditioning on. There's some thought, I guess it's still, there are people who will argue this, that these sort of prediction markets incentivize people who have inside information about whatever the futures contract is to indirectly reveal that inside information by betting accordingly. Whether that pans out, whether the people with inside information actually have reliable information, all this is questionable, but that's one of the motivations for setting up a futures market like this. And these days, there's futures markets for a lot of stuff. That, at a minimum, you could use to help inform a prior distribution about the unknown that's at issue when these futures contracts are created. Any questions about this or its possible applicability of Bayes' rule to it? Yes.
I was thinking a possible thing that I was thinking about is the conventions are gonna be happening soon as well too. So I was thinking it would be kind of interesting to see how that might have an effect when it comes to public morale and
yes.
all of that. Yeah.
So unfortunately, although those are soon, not soon enough for us end of the semester. But it's if you click on this link later in the summer, you can keep up with what's happening. In particular, conventional wisdom among pollsters is that polling only becomes, reasonably predictive after the conventions have happened, which, usually conventions don't really reveal any new information, but they create a lot of attention.
Oh yeah, for sure.
Anything else? Alrighty. So what are hierarchical models, which is the subject of this week and also next week? In Bayesian terms, so from a Bayesian perspective, we're talking about here this semester, a hierarchical model is relatively simple. It's nothing more than a model where your prior on one parameter depends on another parameter, and that other parameter is also going to have a prior. So we've seen this before, at least with hierarchical data, even back when we were doing bowling. We would have a distribution of the second roll in a frame of bowling, conditional on the first roll. And then we would have a probability addition for the first roll of a frame of bowling that ideally would also condition on the bowler's ability. But by multiplying the marginal probability for what happens on the first roll of a frame of bowling times the conditional probability for what happens on the second frame of bowling, given that 10 minus x1 pins are available to be knocked down on the second roll of a frame of bowling, we get a joint probability distribution for how many pins get knocked down in a frame over the two rows using general multiplication rule. We also saw this on homework 3, I guess it was. How many vetoes get overridden? Well, that depends on how many bills get regularly vetoed. And then you have a probability distribution. We did negative binomial or something for the probability of a bill getting vetoed, and then binomial for how many vetoed bills get overridden, given the number of vetoed bills. But we've even seen this in linear models, so that we didn't make much of a big deal about it at the time. We have the errors in a linear model being normally distributed, expectation 0, given sigma. We're not actually given sigma. We're given a prior distribution for sigma. But this would be a fairly simple hierarchical structure for the epsilons. You multiply your exponential prior PDF for sigma by your conditional normal distribution for the errors. Given sigma, you get a joint probability distribution for sigma and epsilon sub n, and all the epsilons are independent of each other, conditional on sigma, so you get a joint distribution for sigma and all the epsilons. But really, we're just using the rules of probability, in particular the multiplication rule and the addition rule as well, except if we do this with continuous parameters we usually take to be continuous, then the addition rule becomes the integration rule. So if we want a joint prior distribution over, say, theta and phi, we could specify that. We could integrate out the phis to get a marginal distribution for theta. But the way in which we usually construct a joint distribution or a joint PDF for these things is by specifying a marginal PDF for one of them, let's say phi, and a conditional PDF for the other one, theta, given phi. We can still integrate out either phi or theta to leave a marginal distribution for the other. And so hierarchical models from a Bayesian perspective. From anti-Bayesian perspectives, it may look a little bit different, but from a Bayesian perspective, we're just doing kind of a special case of what we've been doing for a while, but now our prior for one unknown can depend on another unknown, which in turn has its own prior distribution, marginal prior distribution. And then we combine those together either by doing it analytically or more commonly doing it with draws. Get a joint distribution for both parts, both or all parameters in the model. And then, when we're working with draws, if you don't really care about one of the parameters, then you just don't worry about that column. But the variability in that column of the thing you don't care about is not independent of the variability in the other columns which you may care about, or some function thereof. And so the uncertainty in one parameter gets propagated to other parameters, to functions of those parameters, and so on. So in that sense, hierarchical models are a relatively simple concept if you've understood well what we've been doing this whole time, starting with bowling, simulating, MCMC, conditioning, updating, predicting. If you've understood all that as well as you should, then understanding this additional step for hierarchical models is not that much of a stretch. So any questions about that so far? Okay. So one example of a hierarchical structure, although it's not often thought of that way, is a spline. So we've talked a lot about linear models, and maybe not emphasized enough that linear models are linear because they're a linear function of the coefficients. You could always include whatever nonlinear function of the predictors you want, and we've actually done that. We have interaction terms where some subset of the columns of X are products of other columns of X. We've done, polynomials, or not, I think we've just done squaring. But you could square one column of X to make another column of X. And obviously you could do that with higher order polynomials than just squaring, although that's not really a good idea. We've also done it with dummy variables, like you have one column in your data frame that's like what state do you live in, or some other categorical variable, and then we make that into dummy variables, excluding the base case. And so we've sort of made a bunch of columns out of one predictor with a nonlinear function mapping categorical levels of a factor to dummy variables in X. But a spline is a preferable way to allow a continuous predictor to influence eta in a generalized linear model in a continuous but not linear way. And that's done through this thing called basis functions. And honestly, I think this is talked a little bit more about in the reading for next week than it was for this week. But it's a good place to start learning about hierarchical models. So you take one continuous variable in your data set, apply a bunch of basis functions to that, and create a bunch of columns in X. And so then you're still estimating a linear model in the sense that it's linear in the coefficients that get multiplied by the columns of X, but it yields eta in a GLM, or if we just want to think about this as linear, it changes the expectation of the outcome in a nonlinear way with respect to the predictor. So polynomials are one type of basis function, but there are other types of basis functions that also yield this nonlinear stuff that are better in a variety of ways. So you can follow along with this if you want, if you just source in from week 7 the macroeconomic data that we've been using several times so far. And the spline stuff in RStan-ARM is derived from the spline stuff in a confusingly named package called MGCV that has been maintained for a long time by an even more confusing maintainer named Simon Wood. But anyway, that actually comes with R. That's how old it is. And so you don't really need to do this very much, but you could call that in order to create the X matrix, where you've indicated with this S function of X business that you want X to have a spline relationship to the outcome. Here, X is the change in the unemployment rate for that quarter. It's the same syntax in BRMS, so it's also leveraging this machinery, which is a bit mysterious, honestly, in the MGCV package to set up the X matrix. And once we have the X matrix, then we're good. So that's going to include an intercept by default. We usually get rid of that in order to use our own intercept. And in this case, the X matrix comes out to be 215 rows by 9 columns. 215 because that's how many quarters of data we have there. 9 columns because by default 9 basis functions are included. The S function has a whole lot of options. This is just like the default version of them. So you can get different things, but by default it spits out 9 columns in this case. And you might say, well, why would we be interested in modeling GDO as a continuous but possibly nonlinear, or in general nonlinear, function of the change in the unemployment rate in a quarter? And Art Oken, who is the name, he didn't call his stuff Oken's Law, other people called it Oken's Law after he discovered the empirical relationship between GDP growth and the change in the unemployment rate. But Oken, nor anybody else really, said the relationship was theoretically a linear one. Oken estimated models that assumed linearity, but didn't provide any theoretical reason, at least not in advance, why that would be the case. And that is an extremely common thing in the social sciences. Very rarely will you see something in the social sciences as a theoretical reason to prefer a particular functional form. So you can go for a long time reading stuff in social science journals and never see any sort of nonlinearity in the models, or maybe an interaction, maybe a squared term, something like that, but very limited. But these models that people 99% of the time are estimating are linear models or generalized linear models. But that is not entailed by whatever theory it is they're trying to test. That's just assumed by the software in order to make estimation easier. And in particular, it was assumed by the software in order to make estimation easier, like in 1970 or something like that, when, you know, if estimation wasn't easier, it would be impossible. So there's not much reason, theoretically, to be exclusively relying on linear, generalized linear models. It is quite possible that there is a monotonic relationship between GDO and changes in unemployment rate during the quarter, which would be interesting even if that monotonic relationship was not linear. So usually in the social sciences, to the extent there is any theory at all, it will be saying, okay, the relationship between this and that, conditional on some other things, maybe should be a positive, increasing relationship, or in this case, a decreasing relationship. But there's almost never a theoretical reason why you should assume the relationship between some outcome and some predictor is linear with respect to that predictor, in which case it's bizarre that social science journals are filled with articles that purport to test or undermine or support or whatever a theory using stronger assumptions in their estimator than what the theory entails. And so if you estimate a linear model according to, you know, some substantive theory, and you're like, it doesn't fit so good. That doesn't mean the theory is wrong. It just meant you estimated an overly restrictive linear model when maybe some kind of a nonlinear model would have fit the data better and been just as consistent with the available theory. All right? So by utilizing splines, we can go beyond assuming these linear relationships between outcomes and continuous predictors. All right? Questions about the setup here? Okay. So for these models with the spline, what does the math look like? So here we're going to assume continuous outcome as well. This is all the same as what we've seen before. Only difference being when we multiply the betas, we're not multiplying them by the x's directly. Rather, we're multiplying them by the little kth basis function of x. So these b functions are going to be continuous, and usually they're also differentiable functions of continuous predictors x. Now I should say it doesn't make sense to estimate a spline relationship on a dummy variable, because it can only take values 0, 1. Doesn't even really make sense for a count variable, because the splines kind of assume this is continuous, but that's maybe a little bit of a borderline case. As usual, we have an intercept. Oh, I didn't mention it before, but these columns of x are always going to have a mean of 0 anyway, so I didn't mess with the thing that I usually do of substituting the intercept. But what's different, so we got this difference here. We're weighting with beta a spline function of x instead of x directly. But what's different is my prior on the betas, which are assumed to be normal, expectation 0, okay, that's what we've previously done. But now there's, in my prior for each of the betas, another parameter, sigma sub beta, that's unknown. And so I need to have a prior on that, such as exponential. So this right here is the hierarchical structure for beta that makes splines a form of a hierarchical model. The marginal distribution of the case beta is not normal. It's heavier tailed than normal due to the uncertainty in sigma propagating its way through. But these basis functions and this way of constructing the priors has the property that to the extent the betas differ from 0, then the function becomes more nonlinear. And so that enables the function of x becomes more nonlinear. And so that enables me to specify prior information on the betas through my prior on sigma beta, where if this sigma beta is larger, my function is going to be more nonlinear. If this sigma beta is smaller, my function is going to be better approximated by a single line. But in the end, I'm going to be estimating the posterior distribution of sigma beta. So in technical terms, I'm estimating the wiggliness of my nonlinear function. Yes?
So how would it know how to partition up the function based off its nonlinearities?
Well, the MGCV package and other things that do this, they have the basis functions built in.
Oh, okay.
So you make like 9 different basis functions of the same predictor, and then you weight them by coefficients, and if like a bunch of the coefficients are kind of far from 0, then you can get a very nonlinear thing. Now, for most things in the social sciences, it's probably not wise to have a prior distribution that tolerates a whole bunch of nonlinearity. For most of the things that you want to do in the social sciences, you're probably looking for a relationship that is a little bit nonlinear. Maybe it's like kind of quadratic in the sense that it curves once, but unlike things in physics or some other things that we could contrive that are not social sciences, there's no situation in which you're looking for a function that's like that. Or a pendulum, which is like a pendulum is actually very regular, but it's not
Two
linear.
pendulums is.
Oh, that are hitting each other and.
Like one pendulum on top of another pendulum. It's very
Okay.
track.
That's not social science.
Oh, I forget who that was.
But as we said before, mathematically speaking, everything we have over here on the left is valid for any positive value of sigma beta. But substantively speaking, it is not scientifically useful unless the betas are reasonably close to 0. Now we're going to condition on the data, get updated posterior beliefs about all of this, and so we can update our beliefs as to how nonlinear this relationship might be. But sort of the affirmative case for using priors in a scientific analysis, you as the social scientist know that the relationship is probably not exactly linear, but it's probably closer to linear than to crazy. And so you have to communicate that to the model through the choice of priors. Because mathematically speaking, this is valid for any positive sigma. But almost all positive sigmas are going to create nonlinear functions that are so crazy that they are not scientifically useful. And so we want to diminish the probability on those crazy things with the use of at least weakly informative priors about these sorts of things. So how will we draw? Same sort of thing pretty much that we've already done, except because beta is of size k, I make a matrix for it. Mean zero, standard deviation depends on the realization of sigma beta. And then to form predictions is pretty much the same as we've been doing. I'm slightly clever about multiplying the x's by the respective coefficients. Got an epsilon, add the mu to the epsilon, and that's our prediction for the outcome. Only a slight change in what we've been doing before gets us a lot of flexibility in terms of modeling the relationship between an outcome and a continuous predictor. Really too much flexibility unless we kind of put a lid on the crazy by having a weakly informative prior on sigma. So how will we do this? Well, in RStanArm, like I said, in BRMS, it's really the same syntax with this S business, and it's going to get outsourced to MGCB to do it. But in order to do it with the RStanArm package, we call the stan_gam4 function. It has a default prior with normal on the spline stuff. So I really only explicitly specified my prior on the intercept and the sigma epsilon, and just left me with my default prior on the spline stuff. And I quickly get back this summary of the draws from my posterior distribution, conditional on my observed data. And many people in the social sciences and elsewhere would look at this and be like, I have no idea what any of that means, because I don't know what the fourth basis function being used by MGCB is. So how can I do anything with this? I kind of get intercepts, I kind of get sigma epsilon, that's similar to what we were doing before when we were estimating linear models. But like, how do I interpret this? Why are there no stars? Yes.
Is it just a measurement of linearity for each basis function?
Non-linearity, really, or to the extent it's close to zero linearity. But these are not independent of each other. And so to look at, this one in isolation from all the other ones, like I said, that really only works with extremely linear flat models. So what are we to do? Well, we can call the plot nonlinear function, which has on the horizontal the x, the change in the unemployment rate, has on the vertical eta, or not eta, but the s of x. In this case, eta would be this shifted over by the intercept. And I could have other stuff. I could have other stuff that I'm willing to assume is linear. But in this model, I just had my one spline and the intercept or whatever. And the posterior distribution of my unknown continuous but not necessarily linear function can be plotted. And it is plotted. And it is easy for you to call to make this plot. And as it turns out empirically, it actually does seem to be pretty close to a linear relationship. Maybe the kink in the line might be somewhere around here when unemployment increases by like 2% or something like that in a quarter. Maybe we have a linear relationship with a slightly different slope than what, you know, is more typical of a quarter with smaller changes in the unemployment rate. But we didn't assume the relationship to be linear. We updated our beliefs that the relationship is mostly linear, but it might be two lines going on here. One for like up to there and then another one. So we found that rather than assume that. Or Oken assumed that, and we found that that was probably not horrible for somebody doing this in the 1960s or whenever the heyday of Art Oken was. Right? So as we said before, you should not hope to be able to interpret parameters, particularly not in isolation from all the other parameters. That doesn't even work in a logit model without the hierarchy or the spline or any of that. But we can query models. We don't query individual parameters. We query models that depend on multiple parameters. And if we need to know how the change, you know, in the expectation of the outcome depends on a predictor, we can plot that. We can even plot that with ribbons to depict our posterior uncertainty. So we're much more certain about the relationship, much more certain that the relationship is very close to linear for small changes in X, which are fairly typical within one quarter. Out here, much less data, also up here, much less data for extreme changes in X, and consequently we are considerably less certain about what the relationship is. In relative terms, I think we're fairly, you know, certain about it. But we're more certain around here where the error uncertainty in the posterior distribution is more narrow than we are in here where the error uncertainty is much wider. Now you may have seen plots like this before. Indeed, ggplot, if you do geom line or something like that, it calls MGCV and it will make a thing that looks similar to this. However, MGCV is not really using Bayesian methods, and so these things that you see when ggplot does them, they are credible intervals of the prediction rather than Bayesian posterior intervals for the unknown function. And so even though people, whenever they see something like this with ribbons, they're like, oh, this is the uncertainty or whatever. Technically speaking, not even technically speaking, just speaking, that's actually, those are frequentist intervals saying if you randomly took a different sample of data, you know, and constructed these bounds, then in 95% of the data sets would the true function be lying within the intervals that you construct for reasons that we talked about in homework 2 and, you know, elsewhere and whatnot. That's not really the same as the Bayesian interpretation, which is considerably more intuitive and relevant, particularly in this case where we're using historical data. Nothing is being randomized, so there really isn't a frequentist interpretation, even though ggplot will spit out something that looks like this if you call geom line. All right. Okay. So another form of spline that's actually not in the MGCV package but can be used is a restricted cubic spline. So these splines are less flexible than the default splines in the MGCV package, and that might be a good thing. So it is, I think, often reasonable to make the assumption, even if it's not strictly speaking correct, that a nonlinear function approaches a linear function as it gets to the extremes of the data. So like I said, that may not be exactly correct, but at the extremes of the data, you have so little information at like the biggest and the smallest point, that you can't really reasonably estimate with any precision any sort of unrestricted continuous function out on the edges of your observed data, because you just don't have that much information constraining the function. And so what a lot of people advocate is just say, okay, out there, let's make a simplifying assumption that it approaches a linear function past the endpoints of your observed data. But in the interior of your observed data, let's construct a piecewise cubic polynomials and then join them together. So not only is it continuous, but as it comes to the left and it comes to the right of a knot, they agree in the first two derivatives. So this is essentially cubic interior and linear past the edges of your observed data. It's often a reasonably good assumption to make, and it gives you a spline that has a little bit less flexibility, which, like I said, could be a good thing. And the restricted cubic spline business can be obtained by restricting the derivatives of the cubic polynomial in the interior. And so in order to set that up, you can call the RCS function in the RMS package. So RMS stands for regression model strategies, whereas RCS stands for restricted cubic spline. Don't get the acronyms confused. Anyway, same stuff. Now I'm doing it with Stan LM. So I put the prior on the R squared. In this case, and in a lot of cases with hierarchical models, you do sometimes need to increase the adapt delta, which I think we mentioned before, but we didn't actually have any examples where that made any difference because the models were not producing any divergent transitions. As we get into more complicated models this week, next week, and as you go on in the future, it may be the case that you need to increase this tuning parameter to a higher value. It causes the physics simulation that Stan is doing to draw from the parameter space using MCMC to take smaller steps. And so when you get a warning, and you will eventually, that there have been, a few divergent transitions, Stan is telling you, I missed part of the parameter space because I was taking too big of a steps, and I don't know what was going on in that puddle that I stepped over. And so is fairly simple thing that you can do about that. Increase adapt delta is going to take smaller steps, and thus it'll go through the physics, not missing any parts of the parameter space. Because if you miss part of the parameter space, you are going to get answer that is wrong in the sense the draws are going to be different from what the analytical solution would be if the analytical solution were possible, which in this case it really isn't. But it's telling you I missed part of the space. And so can increase the value of adapt delta, tell Stan to slow its roll, and thereby get good draws from the posterior distribution. In this case, we get draws here, and we get some stuff, intercept, and then x, and the derivative of x, and the second derivative of x, and the third derivative of x again. What do I do with that? Well, you could, call posterior EPRED, and then see how the expectation of GDO varies as x changes when weighted by the coefficients on these four things. You would get, in this case, a function that is close to linear because, well, all this stuff kind of cancels itself out and you're left with a mostly linear function. But that's not obvious from this. It is obvious if you plot it, but anyway. So that's a couple options you can do for splines. Another option, which is very much favored by Bayesians, is to use the so-called Gaussian process. So again, this is something that's mostly talked about in the Michaelis reading for next week. But you can think of a Gaussian process in a couple of different ways. The way that makes the most sense from a Bayesian perspective is a Gaussian process is a prior over continuous functions. Now, the reason why this should make sense from a Bayesian perspective is because back second week, or second, third, fourth, when we were talking about probability, we emphasized that random variables are functions. They're functions from a sample space or a parameter space to some subset of the real line, etc. And so when you put a prior on theta, if theta is interpreted as a random variable from the Bayesian perspective, you're expressing a prior on a function. Gaussian process takes this a step farther. Instead of being a prior over like a scalar parameter that's a random variable, it's now a prior over functions that are not discontinuous. So it has to be continuous. Certainly there are many discontinuous functions, but that's not something that we would really ever anticipate in the social sciences. And that's mathematically and it'd be impossible really for Stan to estimate a discontinuous function because it needs the derivatives in order to do Hamiltonian Monte Carlo. So anyway, Gaussian process, you can think of it as a prior over smooth functions. However, Gaussian process, the observations are not conditionally independent of each other. And so evaluating the log likelihood requires on the order of n cubed numerical operations to evaluate the log likelihood. And so if n is like 1,000 cubed is already possibly prohibitive for data sets that you might encounter in the social sciences. And the BRMS package, it allows you to do genuine Gaussian processes if your data set is sufficiently small. And the data set that we've been using only has like 215 observations. I could have done a genuine Gaussian process, but the BRMS also includes an approximation to Gaussian processes using basis functions, not exactly the basis functions in the MGCD package, but basis functions nonetheless. And so basically you can approximate your GP with a spline, and when you do it that way, it's basically not any more complicated than what we've done on the previous couple slides. And so this construction here in BRMS says to use 5 basis functions. There's also an additional tuning parameter that BRMS recommends that you set to like k divided by k minus 1, something like that, which in this case would be 5/4. We get some default priors that are not obviously good, but we could certainly change the prior on the intercept and on the sigma. We know how to do that. These default priors on the parameters that go into the Gaussian process and the Gaussian process approximation are harder to choose because they're harder to interpret. So BRMS does make a little bit of an effort to choose good default priors in this. It may or may not achieve that, but we'll just go with it mostly in this case. So if we wanted to do a Gaussian process approximation relationship between GDO and the change in the unemployment rate, BRMS can do that relatively easily. There would have been some divergent transitions if I used the default value of adapt delta, which is 0.8 for BRMS. So I had to bump that up to 0.9 in order to make the sampling go good. But once it did, it was fine. I was getting good R-hats here, good effective sample size. But like, what do I do with this posterior distribution? where I didn't even really understand the parameters to begin with. I understand intercept, I understand sigma, which is similar to what I was getting before, but like, what's all this about other than it pertains to the nonlinearity or lack thereof of the function that I was estimating. But BRMS also facilitates you understanding the posterior distribution of the unknown function that you estimated by plotting the conditional effects, which we've done before with like ordinal and monotonic or whatever. So I should say the Gaussian process and the splines or whatever, in this case, they came out to be almost linear. They do assume that things are continuous, but they don't assume that things are necessarily monotonic. It just worked out that way in this case. And moreover, they came out essentially linear in this case. But that's something we found, not something we assumed. And so yes, we can plot the relationship between x and GDO as the posterior distribution of the Gaussian process approximation that we estimated, and found this relationship for which the plot is substantially more informative and useful than knowing that the standard deviation of the Gaussian process has a posterior expectation of 12.58, and the length scale of the Gaussian process has a posterior expectation of 0.32. Other than this being a relatively small number, which is consistent with this being an essentially linear function, that's about as much as you can do with it. So like I said, a picture is worth, at least 1,000 words, and really a lot more when we're talking about Bayesian stuff. But if you wanted to know the function, didn't want to assume that it was linear or quadratic, it's certainly not quadratic in this case. We can estimate that under pretty minimal assumptions. The relationship is continuous, and get updated posterior beliefs as to what the function is. And it is pretty linear, looks pretty linear in this case. However, it is usually not a good idea to estimate one of these nonlinear functions and say, oh, that looks pretty much linear. Oh, that looks pretty much quadratic. And then I'll fit a model that assumes that particular form. And the reason why that's not really a good idea is because actually we have a considerable amount of uncertainty as to what the function is out here where we don't have much data. And so yeah, it looks pretty linear, honestly, all the way up to, in here. But this is saying the true function could be like anywhere in here, with 90% probability. So yeah, this like almost straight line is consistent with that. But, so is this, technically. Now, we don't have any real reason why that would make sense. But by estimating one of these nonlinear functions, propagating the posterior uncertainty, now my uncertainty in the parameters is propagating through to my uncertainty in the function. And so pretty much never are you going to be in a situation in which you can be sure that your function is, exactly linear or exactly quadratic or whatever over all possible values of your predictor, continuous predictor. And so in some ranges of it, you're going to have enough uncertainty that it's good to at least go with the more general form and say, okay, if we had an increase in unemployment rate of 5% in a quarter, I'm not exactly sure what's going to happen because that is so rare that, we've only really observed that a couple times. We're not going to be so sure as to how that's going to change GDO. It's not going to be good, but we don't know exactly. So propagate uncertainty about the parameters through to uncertainty about the function helps you stay calibrated particularly for these situations in which you don't have a whole lot of data to inform what the function is. All right? So that's 3 different but pretty similar, actually, ways of utilizing splines. Now, to the extent that you've heard about splines in the past, you most likely associated them with what supervised learning does, which, historically speaking, really makes no sense. Bayesians were talking about this a long time before supervised learning became a thing. But supervised learning, because it's emphasizing ability to predict, a natural way for supervised learning to differentiate itself from frequentist stuff, which tended to be linear models, generalized linear models, is to say, well, could we get better predictions by relaxing the assumption of linearity? And in a lot of cases, you can. And so splines have been something that supervised learners make use of. But you still have the problems that we were talking about before, which is supervised learning almost invariably will obtain point predictions of these parameters in the training data. They'll waste the testing data, and they won't propagate the uncertainty in the parameter, the point estimates, through the function. And you really need a whole posterior distribution, all, weighted all draws in order to get something that comes out looking reasonable. Now, it definitely is the case that splines with like L1, L2, other forms of regularization are much better than splines from a frequentist perspective. So just maximum likelihood or whatever, no penalization. That is a disaster, usually, because they don't restrict the craziness of the function. They dramatically overfit whatever data they have. They yield terrible predictions for future data. And so the supervised learning people are correct in that their way of dealing with splines much better than the frequentist way, and the frequentist way is so bad that it's not even used, doesn't even use splines that much. But the frequentist, it's still producing point predictions rather than marginalizing over the posterior distribution of all these parameters that Bayesians are putting hierarchical structure on. And thus, it's not as rich and not as well calibrated as what Bayesian versions of splines yield. Right? So don't get confused about that. Now, frequentists do have a version of hierarchical models that has a very specific meaning. When I said from a Bayesian perspective, Gaussian or hierarchical model is nothing more than you have a prior on some parameter that depends on another. That's a sort of very general sense in which Bayesians understand hierarchical models. And most Bayesian models that you see in the literature, of course, there's not many in the social sciences, but in the applied statistics literature, they're mostly going to be hierarchical in some sense, because that is like awesome. We've spent a lot of time this semester trying to make the log likelihood be like the log likelihood that frequentists maximize, or try to choose priors that is, consistent with how supervised learners do L1 regularization or something like that. And we're just sort of now getting into situations where it's like, well, why don't we, since we have like Stan and all this stuff that we've built up that's so good, start doing things that other people can't do well with their methods. It just took us the better part of 3 months to get enough understanding under our belts to be able to start to do stuff like this. But there is such a thing as frequentist hierarchical models. They just mean it in a much narrower context. So in order to understand what that means, we have to distinguish between cluster and stratified random sampling. So what is cluster random sampling? With cluster random sampling, you sample randomly J so-called large units from their population, and then within each large unit, you sample N sub J small units from the jth large unit. And so the canonical example of this comes from educational research, whatever, where the big units would be schools and the small units would be students within schools. So let's say you did a design where you sampled J equals 100 high schools from the population of high schools in a country. And you went to each of those 100 high schools and you sampled 20 students from each high school. You would have a total sample of 2,000. But you would not have a simple random sample of 2,000 students from the population of students because your 20 students were clustered in J schools. J is 100 or whatever you set J to be. But the important thing about cluster sampling is you're sampling a subset from all high schools. You're not going to every single high school in the United States, just J of them. And so you have randomization at 2 levels. And that affects any estimator that is applied to the data. And in particular, it is completely at odds with the assumption that the students are a simple random sample of high school students when they only come from J schools, or the J schools were realized. And cluster random sampling is contrasted with stratified random sampling, where you divide the entire population of large units into J, mutually exclusive and exhaustive, subsets, subgroups, and those strata are not random variables. But you go within each J large unit, sample N sub J small units from the Jth large unit. So canonical example of this would be like political polling or something like that, where you divide the population into large units such as J equal 50 states, or 51 if we want to count District of Columbia as like a state. Those are not random variables. Like the existence of New York, not a random variable, or any other state. Moreover, we're not just looking at a sample of states. It wouldn't really make sense to do in most cases as a political poll. Oh, I'm going to take a sample of 20 states. And then I'm going to take 100 people from within each of those 20 states. Because the answer that you get is going to be way too sensitive to which 20 states get realized in your study. So you take 20 states randomly out of 50 or 51. Sometimes you're going to get like 8 states from the South and only 2 states from the Midwest or something like that. And so that would be a not good way to make inferences about the population as a whole. And consequently, pollsters don't do that. A lot of times, if they're doing a national poll, well, they'll go into each of the 50 or 51 state-like places and then sample some N sub J number. This doesn't have to be the same for every big unit. So what you'll see a lot of times, N sub J for California is going to be a bigger number than N sub J for Wyoming, in order to make it come out at the end that we're giving like more weight to California than we are to Wyoming, because California has a lot of people and Wyoming has a lot of like elk and stuff, but not really people. So they don't have to be the same number, but the American National Election Study and all that, they're going to sample people from every state and the District of Columbia in order to get something that comes out at the end intended to be representative of the population of voters as a whole. But these are very different, both substantively and from the perspective of estimation, particularly frequentist estimation, because in the case of cluster random sampling, our schools were randomly sampled. Whereas in the case of stratified random sampling, the states are not random in any sense, and moreover, we're including every subgroup in a stratified random sample in our study. If we were to repeat this study again, we would do it with the same 51 states. We would just randomly change the N sub j voters in each state. If we were to redo this, we would get j different high schools in the first stage, and consequently also like N sub j different people, students, in the second stage. So these have very different consequences for the distribution of the estimator across studies, which is really what frequentism is all about. What if we were to do this study over and over and over again? What would be the distribution of the maximum likelihood estimators? Very different depending on what you assume about whether the big units are random variables or not. Okay, so this allows us to think about models that have group-specific intercepts. So let's let alpha be a common intercept, sometimes known as population intercept, and beta be common coefficients. And then A sub j is the deviation from the common intercept by the jth big unit. And so we could write a linear model, or this could be a GLM, but let's just say linear like this, where the outcome for the ith small unit inside the jth big unit is equal to the population intercept plus the weighted sum of the coefficients by whatever predictors you have at the small unit level, plus A sub j, plus the error term, which is specific to the ith small unit within the jth big unit. And that equation is the same from a Bayesian perspective and a frequentist perspective, but they have extraordinarily different interpretations of it. Because from a Bayesian perspective, the expectation of the outcome, given the predictors, and the fact that the ith small unit is within the jth unit, is alpha plus the weighted sum of the x's plus A for the jth big unit. That leaves, from a Bayesian perspective, the error term, which we can assume is normal or whatever, epsilon, and it depends on the ith unit within the jth group, etc. Frequentists see things differently and weirdly, but from a frequentist perspective, the expectation of the outcome for the ith small unit within the jth big unit, given x, but irrespective of the fact that this small unit is within the jth big unit, is just this piece here with the population stuff, alpha plus the sum of the betas times x, leaving A sub j as part of the error term along with epsilon. And so from a frequentist perspective, the problem with cluster random sampling designs is that the error term is not independent of each other. And to be more specific about it, the error for all 20 students within the first high school is going to be usually positively correlated due to whatever idiosyncrasies were going on in the first high school. It's principal, it's neighborhood, all sorts of other stuff that affect all the students in that high school, giving them a common component to the error term. And so from a frequentist perspective, in cluster random sampling designs, it does not make sense to assume that errors are independently and identically distributed, when if you all came from the same high school, your errors are not independent of each other because you're influenced by the same administration and the same set of teachers and, you know, whatever else might be going on. And so from a frequentist perspective, cluster random sampling designs, although they're very cost effective, make it impossible to assume that the errors are independently and identically distributed because we have dependence of the errors within the jth big unit. From a Bayesian perspective, which as usual makes more sense, we're conditioning not only on the predictors, but the fact that these, you know, you all hypothetically came from the same high school, you're in the same big unit. And so we're going to condition on that fact, include A sub j as part of the expectation for someone in the I small unit within the j big unit, which just leaves the epsilon piece left over, and that we can assume is independently and identically distributed normal, or, you know, we can make other assumptions about it, but we can assume it's independent, unlike the frequentist case where A sub j is part of the error term instead of part of the expectation. So that's a rather subtle point, but it's an important one, especially when thinking about the difference between frequentist estimators of hierarchical models and Bayesian estimators of hierarchical models. Bayesian estimators are going to condition on the group structure. Frequentist estimators are going to marginalize over the group structure because they see A sub j as being error rather than something systematic. Questions about that? All right, so we can also do this with slopes that differ according to the jth group. So let's let everything be the same, but we now have a vector of b's that are indexed by j, and so b sub j is the deviation from the common population level set of coefficients. And so we can write the model like this or like that, which is actually the same equation, but different interpretation. From a Bayesian perspective, all this is going into the expectation of the outcome, conditional on the predictors of the little units, and conditional on the group structure. And so we're going to incorporate into that the deviation from beta, which is represented here by b, and we can have that for any or all of the k predictors. Whereas from a frequentist perspective, not only this, but actually all this is part of the error term. Another reason why the errors within the jth big unit are not independent of each other. And so the expectation from a frequentist perspective, conditional on the predictors, but not the group structure, is just this. So anyway, we can do this with slopes, we can do this with coefficients. Really, with BRMS in the stand, we can put group structure on anything. Even sigma and other stuff, we can say how that varies by groups. That's difficult to impossible to do from a frequentist perspective, but in this model, if you assume normality of everything, it actually is possible for frequentists. Let me go to the next slide. So frequentists assume that the A's, which are the deviation and the intercept by the jth big unit, and the B's deviate from the common parameters, and they're gonna say they deviate according to normal distribution, bivariate normal distribution, multivariate normal distribution if we had more than two things going on. And the variances and covariances of that multivariate normal are population parameters that will need to get estimated, even from a frequentist perspective. However, and this may seem like an extraordinarily technical distinction. The A sub j's and the B sub j's, from a frequentist perspective, are not parameters. Because in order to be a parameter, it has to remain fixed in repeated sampling. And if I repeatedly sampled using cluster sampling, schools, when I do this study, hypothetically speaking, the second time, I'm going to get a different set of J schools. And so that set of J schools is not going to tell me anything about the A sub J's and the B sub J's for a school that I got the previous time I did the study. And so from a frequentist perspective, the alpha and the beta and the variances and the covariances, those are parameters. They remain fixed every time you do the study. But the A's and the B's are not parameters because their values change every time you repeat the study, because you get different schools, and different schools have different A's and B's associated with them. And so the reason I say this is extraordinarily technical but important distinction, if A's and B's are not parameters from a frequentist perspective, ergo, they cannot be estimated. They can only be predicted given estimates of alpha and beta. Basically, you integrate out all the junk, estimate alpha and beta according to maximum likelihood, subtract the expectation from y, and like do some stuff with the residuals to come back with what is known our best linear unbiased predictors, not estimates. So they are blups rather than blue predictors of A and B. Now, this highly technical distinction is completely lost on 99% of the people who use frequentist estimators of hierarchical models. But it makes them extraordinarily confused as to why they don't have p-values for like A sub j. Well, in order to have a p-value, you have to be an estimator. In order to be estimated, you have to be a parameter. And A is not a parameter, therefore it cannot be estimated. Therefore, it does not have a sampling distribution across studies, ergo, no p-value, ergo, no ability to test whether A sub j is statistically significantly different from 0. All the other stuff that frequentists habitually, or people who use frequentist methods, habitually use. But because these are not things that can be estimated, what frequentists do is something that seems awfully Bayesian. They integrate them out of the likelihood function with respect to a multivariate normal distribution that they call an assumption rather than a prior, because if it was a prior, it would be Bayesian. And so they integrate out the A's and B's, which is possible to do analytically if you assume everything is normal, to obtain a new likelihood function that only depends on the alphas and the betas and like the sigmas, not the A's and B's. Choose alpha and beta to maximize that, and now you have maximum likelihood estimates of the population parameters and the ability to predict the A's and B's, which frequentists refer to as random effects, in a so-called mixed effects model that includes both fixed parameters to estimate known as fixed effects and random effects that go into A and B that contaminate the error term, make it not independently and identically distributed within big units. Now, going back to this distinction, from a frequentist perspective, if you buy all the other stuff about frequentism, including especially the interpretation of probability as, you know, the probability of something is the proportion of times it happens, and the limit is the number of randomizations goes to infinity, that stuff. From a frequentist perspective, if you have a cluster random sampling design, you must use hierarchical models because you need to integrate out the random effects from the large units, which are still realizations of random variables from the population of large units, in order to get good, basically, you know, consistent and asymptotically normal point estimates of the fixed parameters. But if you have stratified random sampling design, you must not use hierarchical models, because from a frequentist perspective, hierarchical models require that the large units be realizations from a population of large units, or a sample. Whereas in the case of stratified random sampling, not only are the large units not randomized, you have all of them. You divided the population into mutually exclusive and exhausted subsets and did a sample of voters or whatever within each of those. So from a frequentist perspective, it is completely wrong to use a hierarchical model which assumes the big units are random variables in a case where the big units are not random variables. Now, from a Bayesian perspective, all that's crap. From a Bayesian perspective, we're going to condition on what we observe. We observe the group structure, and so we're just going to do our thing, which includes putting priors on everything we don't know. That includes the A's and the B's. So you will hear Bayesians, unfortunately, adopt the terminology to refer to the A's and the B's as random effects and the alphas and the betas as fixed effects, which makes no sense from a Bayesian perspective. Like, that distinction between fixed and random effects only makes sense in the frequentist world, where they're thinking of the A's and B's as random variables and the alphas and the betas as fixed constants. From a Bayesian perspective, yeah, you put priors on all the unknowns, but there's nothing more random about the A's and B's in terms of your prior beliefs about them than there is your prior beliefs about alpha and beta and sigma and everything else. You're just putting a prior on all the unknowns, and you're conditioning on all the data. So we could, but we're not going to integrate the A's and the B's out of the posterior distribution, and we're going to get posterior draws of them along with all the other things. So from a Bayesian perspective, hierarchical models are only slightly different from the flat models that we've mostly been emphasizing before. But because they're only slightly different, you only have to learn like a little bit of new stuff in order to do them. Whereas from a frequentist perspective, multi-level models, hierarchical models, those are synonyms, are quite different from flat models, and are quite different from purely fixed effects models that would be appropriate from a frequentist perspective with stratified random sampling designs. And so this is something that's only like covered in advanced frequentist classes that most people don't even take. So they have a pretty poor understanding of what's being assumed there. So either way, you could assume normal distribution, bivariate normals on the A's and the B's. Put this up before, just wanted to remind ourselves of it, that the bivariate normal distribution, or here the PDF of the bivariate normal distribution, can be written as a marginal PDF that's normal for the first thing, times a conditional PDF that's also in the normal family for the second thing. But the conditional expectation of the second thing is in red here, and the conditional standard deviation of the second thing is in blue. We did that before, like way back before the midterm, but I just wanted to remind people of it when I get into the math of the data generating process of a hierarchical model or multi-level model from a Bayesian perspective. And so from a Bayesian perspective, this is potentially applicable to either cluster random sampling or stratified random sampling, or really any other design where we have big units and small units. Okay, so linear model doesn't have to be that way, but we got eta, we got n. We got the epsilons being drawn independently from normal distribution. Obviously, we have to have a prior on sigma. Our eta we're going to construct as, okay, assume the x's are deviated from their means or whatever, population intercept. plus deviation of the intercept in the jth big unit, multiplied by this sum of the population coefficient and the deviation in the population coefficient for the jth big unit, multiplied by the predictors, or predictor in this case, you could have more than one, who are indexed by their big units. We have priors, let's say normal priors on the population parameters, alpha and beta. And we're gonna have a bivariate normal prior on the A's and the B's. So we're gonna construct our bivariate normal prior as a marginal normal prior on the A's and a conditional normal prior for the B's given the A's with the same construction that was on the previous slide. So if the expectation of alpha is 0, then the conditional expectation of beta is this here, and the conditional standard deviation is that. And so these together are bivariate normal distribution for the A's and the B's, each of them independent across big units, but within a big unit, the A and the B depend on each other to the extent that rho is not 0. We're gonna need prior on the standard deviations for the intercept and the coefficient deviations, and then some sort of prior uniform between -1 and 1 is usually fine, although oftentimes these have positive dependence on rho, which is the correlation between A and B. Question?
I just wanna make sure from my understanding, so B, I guess, depends on A, in that
Yeah.
case, because the school or the district that you select or state you select is ultimately gonna have its own randomness.
Yeah, so you're saying within New York,
Yep.
the intercept from New York is not independent of the slope deviation for New York. Those in general could be correlated. Maybe you don't anticipate that correlation to be too close to 1 or -1, maybe closer to 0 than to 1, but you could reflect that in your prior on rho. But it is rather important to use bivariate normal for these deviations rather than the simpler thing, which would be to assume that rho is 0, in which case these are independent. That's usually not a great assumption. So from a frequentist perspective, it's completely different, although it looks very much the same. Why? Same construction there. Epsilon. So this is coming from a frequentist perspective from a normal distribution, but within the jth group, the expectation of the error is not 0 because of the A's and the B's. Does have sigma epsilon, but instead of putting a prior on sigma epsilon, frequentists are going to take that to be given, even though they don't have it. They don't know what it is. And so the variation is due, the variation in the point estimates is due to the randomness of the big units, and then who gets selected among the big units from the small units, rather than saying the randomness comes from our uncertainty about those parameters. Expectation of eta is only going to, that should be a multiplication there. Only going to depend on alpha and beta, which of course frequentists are going to assume to be given. Same bivariate normal distribution, but very different interpretation. From frequentists, this is part of the error term. It's why that's not having an expectation of 0. Whereas from Bayesian perspective, it's part of the expectation of the jth group. And consequently, the parameters that go into this bivariate normal also going to be taken as given rather than unknowns to have prior distributions. Oh. But because of the superficial similarity, 99% of the people who are using frequentist estimator of a multi-level model are going to be prone to interpreting it like a Bayesian model and not realize or not recognize the fact that because you only get point estimates of the fixed parameters from a frequentist estimator, you're missing out on all the good stuff of a Bayesian estimator. And in particular, you get stuff that is really just telling you the mode or the supremum and not the entire distribution. If you assume the posterior distribution is just normal, then all you need is the extremum to tell you about all the stuff. But in general, with these hierarchical models, the posterior distribution can be rather far from multivariate normal under some circumstances. So let me sign back in, re-render this. While I'm doing that, does anyone have any questions about what we've been talking about? So while that's going, it's probably worthwhile to take a second to think or reiterate that multi-level / hierarchical models from a frequentist perspective, it's a very narrow, albeit advanced thing. It's like how you need to change your estimator when you have cluster random sampling design. Whereas from a Bayesian perspective, hierarchical models are a real general thing. At any time you have your prior for one unknown parameter, depending on some other unknown parameter that you also have a prior for. That's a Bayesian hierarchical model. Now that includes the situations where frequentists, fret about cluster random sampling versus stratified random sampling and like fixed effects, random effects, mixed effects, all that. So it includes that, but it goes way beyond that. Not just including like splines, but farther generality than that, any situation in which you have a parameter. That depends on another parameter, which you do not in the frequentist case because the A's and B's are not parameters. So therefore you don't have parameter depending on another parameter if the A's and B's are not parameters. Even though we can make assumptions from a Bayesian perspective that are essentially the same assumptions as being made here. Moreover, it's essential to assume bivariate normal in order to integrate out the A's and B's from the likelihood function analytically. We didn't have to make bivariate normal. And honestly, like marginally, because of the uncertainty in rho and sigma or whatever, they're not bivariate normal marginally. But we could have done t distribution. We could do gamma distribution if we're sure these are positive or whatever. We have flexibility there. Frequentists really don't if they're going to restrict themselves to situations in which they can analytically integrate out what they consider to be part of the error term. So the LME4 package in R for a long time has implemented frequentist versions of multi-level models, and it has popularized a syntax where you have like one vertical bar G. So this vertical bar in this context does not mean or, like it would mean in the rest of R. It pretty much just means vertical bar. In the sense that it's saying from a frequentist perspective, the intercept is random. The A's are random. And they vary by level of your grouping factor G, where G is known. Like G would be the school name. You can also have a nested business with like more than one thing. So if you had schools within school districts and then students within schools. So you might randomly select 50 school districts. Within each school district, you randomly select 5 high schools. Within each high school, you randomly select 20 people. Some business like that. You could have randomness due to the big units. Well, you have the really big units, which are school districts, and then the slightly smaller big units, which are high schools. Stuff like that going on. So you can have that varying at 2 levels. You can also have these ones where X appears in this little thing, which indicates that not only the intercept, but also the slope varies according to the big units. You have this, which is going to assume that the A and the B are uncorrelated, which is to say fixing rho to 0. That's an option, but it's not really a very good option. So anyway, the LME4 package, very much frequentist, even though people tend to interpret the output in a Bayesian way. but it does popularize a syntax that, for better or worse, both RStanArm and BRMS adopt rather wholeheartedly. BRMS, I think, has some extensions to this syntax. RStanArm pretty much just takes it as is. So if we wanted to use hierarchical structure for a measurement model, going back to our macroeconomic data, if we stack together the GDI and the GDP readings for each quarter, just call that Y. Here we're saying the outcome in each quarter has a population intercept, but we're going to deviate from that intercept in each quarter. And so there are two, well, there's like mini quarters that define the groups, but we're saying there's a random deviation in this quarter and previous quarter randomly related to that. Estimate this with data prior to the pandemic. Use the default priors except for the prior on the intercept. And we get back output that looks like this. So this is its estimate for, or its posterior median of alpha, you know, with the estimated standard deviation around 0.2. So on average, over like all of these quarters, the rate of economic growth tends to be around 3. And the measurement error tends to be around 1.4, which is actually higher than what we were using before. But what's different about this output, we see at the bottom here, we also get a posterior distribution of the deviation across groups, which in this case are quarters. This would correspond to well, we're assuming it to be the same, but the deviations in the A's. There's no B in this model. So the deviations in the A, sigma A, that has a posterior mean of 3.6 according to our model. So basically in the language that we did before, the mu sub t, the true rate of economic growth in a quarter, has a standard deviation around it that's estimated to be around 3.6. We're not totally certain about the 3.6, but that's our posterior mean. So like the truth has a standard deviation of 3.6 across quarters. But even given the truth, we're measuring GDP and GDI with an additional error that has a standard deviation of about 1.4. So the standard deviation of the truth is actually a lot bigger than the standard deviation of the measurement error in GDP and GDI. But since we don't know what the truth is, that yields this sort of fairly heavy-tailed and sometimes confusing distribution of estimates of GDP and GDI, which we examined before on a previous homework. And so it's worth revisiting that idea because 8:30 on next Thursday, U.S. government is going to release its initial estimate of GDP for the first quarter of 2024. It won't give us an estimate of GDI for first quarter of 2024 yet, but it's going to revise its GDI estimates from the fourth quarter of 2023. And so if we were doing like homework 2 or whatever it was again now, you might ask yourself, well, what do you think the true rate of economic growth was in the first quarter of 2024? And to inform that, you might look at things like the Wall Street Journal, which Monday published a survey it did of a whole bunch of economists who mostly work at like JP Morgan and Goldman Sachs and places like that. And those 68 economists had a mean of 2.18 for the growth in the first quarter, with a standard deviation of 0.38. And that's higher than what they used to be predicting a few months ago. And, okay, sure, that's kind of a reasonable basis for forming a prior. These economists are not very good at predicting the economy, but they're not cow sheep bad. you don't have somebody from JP Morgan or whatever predicting 10,000% inflation or 100% deflation, which would mean everything was free. Like, they're not as bad as what we see when we survey randos. But, you know, they're not right. And so the Wall Street Journal had a podcast where they talked to somebody named Sam Goldfarb, who says you can definitely get cynical about these things, say, hey, these economists aren't 100% correct all the time. In fact, they're not even close. So why should we care what they think? But maybe they're not as wrong as you might think. Or maybe they are. Either way, doesn't really matter. Certainly, no one thinks of these economists as objective in the sense of Fisher. Like, can you imagine the Wall Street Journal editor being like, whoa, hold on. You know, this survey that we do every quarter, actually, of these people, they can't prove deductively that it's going to be 2.18. Nothing's being randomized. Frequentist probability doesn't apply. These are all subjective. So we're not even going to write this up as a story. I'll kill the story. I mean, nobody thought they were objective in the first place. But just because they're not objective doesn't mean they're wrong. Or more specifically, it doesn't mean they're completely wrong. Because if they're even a little bit right, that's providing some more information. So the fact that it's almost definitely not going to be greater than 5 and almost definitely not going to be less than 0, that is important information. If the sort of mathematical model says, okay, this is valid for any real number, well, it's not substantively useful if you're predicting a 10,000% growth rate. Like, that makes no sense. But that's mathematically consistent with the model. And so we need surveys like this, and we need prior information to sort of feed into our models to say this is the reasonable area within the parameter space within which we want to update our beliefs to get the posterior distribution. So I got a few more minutes. Hierarchical models are particularly common in psychology, but it's going to differ a bit because in political science and economics, the big units are often going to be countries or states, or in this case, quarters. So more likely to have stratified random sampling designs or not even random sampling at all in the case of the macroeconomic data, but still having group structure where the big units are like really big. In psychology, hierarchical models are common, but the big units are often people. So in political science, the small units are often people. In psychology, the people are bigger. And the small units in a hierarchical model in psychology are often questions or outcomes on repeated tasks. So if you participate in one of these psychology experiments, they will ask you, like, are you depressed? In 20 different ways. And then you'll get, like, you know, a Likert scale or whatever on all the different ways that you basically answered the same question. And so you are a big unit. You're not going to be the only big unit, but there may be not so many big units in a psychology study. But you're going to have variation within big units according to your answers to similar questions. Or if we're doing like the SAT or whatever, you get a whole bunch of math questions. And so, or everybody does. And so the correctness or the severity or whatever of the outcome is going to vary a little bit according to the wording of the different questions, and there are a whole bunch of questions. So in hierarchical models, the syntax, at least for LME4, is usually going to look like this. There's going to be an outcome, some treatment variable that's being manipulated, and we want the sensitivity of the treatment variable to randomly vary from one person to the next, also allowing random variation in the tendency to say like the right or wrong answer or the more severe, less severe answer to vary from one question wording to the next. And so this Right here is what's known as maximal syntax, but it's actually only maximal from a frequentist perspective. We could go with considerably more generality if we were to allow ourselves to use Bayesian estimators, which, we are in this case. But we could also allow like sigma to vary by person if we wanted. You can do that in BRMS. So in psychology, the questions of interest is usually, how do we want to predict the outcome for a new big unit that we haven't observed yet from the same population of big units, as opposed to predicting how well we would predict a new question for the same big people. You could do either way, but usually they want to say, okay, given the conditions, can we predict how depressed a person would be who we haven't seen yet, who's not even in the data. Supervised learning would call that a testing person, but it's really just someone that you haven't observed yet. Can we make predictions about those? And so we can do that with BRMS. You can do it with stan_glimmer and rStanArm as well. This is from like a tutorial that is written with rStanArm, but I'm going to show you how to do it with BRMS. I think this data is actually simulated, but it was like the simulations were based on an actual psychology experiment, but they couldn't get the actual data, so they had to simulate something that looks like the actual data for like privacy reasons or something like that. So I don't exactly know what this study was about, but in my mind, they like got a bunch of people who have person IDs in the data, and they would like hit them with a stick and see how mad they got. Probably that was not exactly how it went, but that's how it went in my mind for this. And so we would have priors on the coefficient on the treatment with hitting people with the stick, and valence is like how mad they got. And then there's variation in the intercept and the slope of that from one person to the next that we would want to put priors on. These are the defaults, which are a bit suspect. We'll talk about this LKJ business more next time, but it's really in the case of just bivariate normal, a uniform prior on the row between -1 and 1. That's the default. So that's all we have there. And so here again is the same math notation that I put up before for a Bayesian model. This is how we would do it with our code. So, we have the rho and the sigma A and the sigma B and the beta and the alpha and the sigma and the errors or whatever. Drop them all those 1,000 times. Cross join them together. What's a little bit different is we're going to group by person ID using the dplyr syntax. Draw A and B for each person, but dependent on the population parameters that we already drew. Make the eta, make the epsilon, add the eta to the epsilon, we get predictions for a person who's subjected to like multiple questions as to how angry you got, or at different points in time, something like that. So we can do this with BRM. Priors, we can take not the default priors, but something maybe a little bit better in this case. I think how mad you got was measured on a scale from 0 to 100, so I put a prior of normal 50-20 on the intercept, and I roll, get back posterior draws that have summaries. So down at the bottom, we have the regression coefficients, the intercept, and the treatment effect for the population level. And then also above that, we're going to have draws that are summarized of the standard deviation and the intercept across people. So there were 20 people in this study. The standard deviation in the treatment effect across people, and the correlation in the deviations, which in this case came out with a posterior mean of -0.2, but a lot of uncertainty around it. It's not too uncommon. So this brings us quickly to doing Pareto-Smith leave one out cross-validation estimator of the ELPD. And what I want to highlight here is that our estimate of the effective number of parameters is essentially 27. But there were 46 nominal unknowns in the model. And the reason why the effective number of parameters is smaller is because we're providing a fair amount of prior information with the hierarchical structure and also having priors on the parameters. Consequently, the complexity of our model acts like a model that has 27 parameters in it, but no prior information, when really it was a model with 46 unknowns and a good deal of prior information. This is particularly common in multi-level models to see the effective number of parameters be much smaller than the nominal number of parameters because you're supplying prior information about the A's and the B's. Finally, we can do posterior predictive checks, and when doing so, it is often good to group by the thing that you grouped by estimating the model. So this is a separate plot of the predictions for each person. And you can see, if you look at this, the model makes a whole lot more sense than the data does. So person like 9, like, I don't know what they were doing. Like they got really mad, then they got really happy, and then they got hit with stick, and they got mad. But the overall trend is like with a positive treatment effect, you get more mad, like more times you get, but there's a lot of noise going on in individual people. It's very common in psychology. It's why you need multi-level models to shrink towards the population person rather than getting overly mixed up by individual idiosyncrasy. Final thing we can do, we can make predictions for a new person that we haven't observed before. You might say, well, how's that even possible? Well, you do it with that syntax, and then what does that syntax do? Well, we've already, we don't observe person 0. So we draw A and B from a bivariate normal prior, given the posterior distribution of the sigmas in the rows. And then we form the expectation with the posterior distribution of all this and the realization of that NBO multiplied by the predictor, whatever it is. Draw the epsilons from a normal distribution with the posterior realization of sigma for the epsilon. Form the predictions. And this process yields a prediction for a new big unit. And this is much better than the predictions you could possibly get from supervised learning or frequentist methods, mostly because they are just dealing with point estimates of the parameters, not allowing the uncertainty in all this, uncertainty in the alpha and the beta and the sigmas, to influence the distribution of the predictors. As a result, they have much worse calibration than what Bayesian hierarchical models do. Okay, overtime for today. I will post the last homework either tonight or tomorrow morning, and it will be due before class next time, which will be a last class, and we will continue to talk more about hierarchical models and their uses for Bayesian estimation, particularly with the social sciences. And we'll also talk about the answers to the homework.
Yeah,